Okay, so good evening, everyone. Uh, Let us start today's session on single solution meta-heuristics. In this, as yesterday we have done, today also the attendance link will be shared. Okay, and we have to give the attendance. And today also one code will be shared on this screen. That code you have to enter as you have done yesterday. So don't be worried. You just focus on the lecture. We shall help you to get the attendance. So don't focus on the attendance. You focus on the this lecture. Okay. So so we can start.
Yes, sir.
Yeah.
Thank you,
Thank
sir.
you. Thank you.
So, what I have planned for today is we will discuss some basics of solution representation and how we understand the relationship between the solution space and the objective function. Before that, yesterday we have missed a small portion of the lecture. We will go through that part, and also I will cover overview of yesterday's lecture because that will be handy in today's session. Okay, so this was the content of yesterday's lecture. So what we did is we started with the workshop details, and what I will do is I will go through the workshop details once again because it will help people to get the materials and all. So yeah, so as per the workshop schedule, on the first day we had some basic introduction. We had discussed about the decision making process. So we discussed about the motivation of studying this optimization problem, and also realizing that we have indeed done basic modeling before. There were introduction to optimization. We discussed the definition, not technically definition, but understood what optimization is, what is an objective function, what is search space, what is objective space. Then we discussed the classification of optimization methods, the exact methods and the approximate methods, and then their further classifications. We understood what a heuristic is and what a meta-heuristic is. Then we briefly touched mathematical programming. We discussed linear programming. We skipped integer programming, which we will discuss now. And we discussed greedy algorithm for traveling salesman problem. And I did not cover this part. Moreover, this part was already scheduled for day 2. So if I go in the details, this part is here, solution representation. So it was already planned for day 2 content. Okay, so today we will cover solution representation, neighborhoods, landscape. Uh, at present, you may not understand these terms, but we will see what it means, local search. And I have also kept the content of simulated annealing in this lecture. If we get time, we'll cover that. Otherwise, we'll take it as planned tomorrow. The workshop materials will all the recordings and slides will be available at this link. You can go to this link and always view this lectures and materials. It will always be available. I will not remove it from my website. So after this end of this workshop also, you'll get the recordings and slides. This is the book I am following for this workshop. If you are interested to read more about meta-heuristics, you can go to this. You can download this or maybe purchase this book and then um, read more about this topic. One important note, in this meeting platform, you will not be able to see a chat option. So if you have any comments or doubts, you can post it in the WhatsApp group. If you have not joined the WhatsApp group yet, please check the mail which Professor Kundu has sent you. You will get the link to join that workshop group and WhatsApp group, and then please join the WhatsApp group. We can communicate there throughout this live session as well as after and before the sessions. This is a brief introduction about me. I'm a PhD scholar in the Department of Management Sciences, IIT Kanpur. These are my email IDs. You can contact me anytime. Okay, so what we'll do is we have skipped. So yesterday we were talking about linear programming, but we skipped integer programming, specifically one problem, knapsack problem. We will discuss that problem, and we will see one greedy algorithm used to solve that problem. And we will also see that greedy algorithm, which we are discussing for the knapsack problem, is actually a problem specific heuristic designed specifically to solve knapsack problem. Okay, so that is the thing we'll notice today. So I'll just jump there. And moreover, we discussed few problems yesterday. So we saw Chinese postman problem, we saw traveling salesman problem, and I don't think we discussed any more problems. So traveling salesman problem is an important problem. Why? Not because you will receive this again and again in your real life, but because we will use traveling salesman problem in our lectures then and now to discuss different topics in this workshop. Okay, so if you are not aware of traveling salesman problem, or if you missed yesterday's part, please go back to the recording and see what a traveling salesman problem is. Traveling salesman problem. So yeah, so we discussed linear programming with that example of two products, and we saw the mathematical formulation, and then we were talking about integer programming. Before that, I have a small tendency of speaking fast. If you think I'm speaking fast, please stop me. I will try to decrease my pace. Okay. So what is integer programming? Integer programming is a mathematical optimization technique where some or all of the variables are restricted to be integers. So we discussed the why we need integer variables. For example, if you have some product and that product cannot be divided. For example, there's a manufacturing company which manufactures aircrafts or large products like you can say cars or something. So you cannot just build zero point 0.5 cars. Why I'm saying large product? So think about a company who is building a chairs or tables. So what you can say is in one period that company is building 4.5 chairs. Then you can say we cannot build zero point 0.5 chairs. Now what we can say is, okay, in one period that company is building 4.5 chairs. So in two periods the company is building 9 chairs, right? So we can take forward that half part and combine it. So in suppose one period is of 6 hours. So in 6 hours that company is building 4.5 chairs. But in 12 hours the company is building 9 chairs. So in that case we can have fractional quantities of products when the products are small. But when the products are large and it takes large amount of time, say 2-3 months or maybe 2-3 years, then it is better to restrict ourselves with integer. One more important note: why are we specifically focusing on integer variables and real variables? Why not take all variables as integer variables? This is important to it is important to realize that when our problem only contains real values, or not values, real variables, then our problem becomes easy to solve. Again, easy in quotes. I'll have not explained what easy to solve is. But even if some of the variables in a problem becomes integer, that problem may become very, very difficult to solve. Okay, so integrality brings more complexity to our problems. Therefore, we try to model more and more problems as real valued problems, even if the variables are not real valued. For example, that chair problem. So for a company, if we are modeling it as a for a company of furniture manufacturing, we may model that quantity of product as real valued, because that reduces the complexity a lot. And suppose you are getting 4.5 chairs in a period, you can just ask the company, consider two periods as one period, and then you can proceed. Okay, so we try to model more and more variables as real variables, that is real valued variables. Okay, so used in scenarios where solution must be whole numbers, yeah, we have discussed this. So we'll see knapsack problem. So this problem is also very intuitive and you can understand it very with real examples. So suppose you are suppose there is a thief. So I've taken this example like this only. There can be many applications of this problem. So suppose there is a thief and he has entered a house at night to do burglary, and this thief has a bag, and this bag is actually known as the knapsack. Okay, this bag has a capacity, suppose it can hold weight W. It cannot hold any more weight. So the maximum weight it can hold is W. Now this thief enters this house and he sees items. Some items are more valuable according to him than the other. So suppose there are some items which he value more and there are some items which he value less. He has to make a choice. His bag has a limited capacity. He cannot steal all the items from the house. So he has to make a choice whether to pick an item or not, because that item when picked takes some capacity in its bag, and each item has some value. So suppose there are n items, item 1 2 3 n. Each item has two you can say two associated things to it. One is the value it holds, and one is the weight it carries. Okay, so you can have value 1 for product 1 and weight 1 for product 1, value 2 for product 2, weight 2 for product 2. So if item 2, he picks item 2, he gains a value of V2 and he loses capacity of W2 from his bag. So the problem is he has to decide which item to pick such that the capacity of the bag is not exceeded. So this is the problem. Okay. So given a knapsack, what is the maximum with a maximum capacity of capital W? There are set of n items. So I have written small n, here I have written capital N, doesn't matter. There are set of items with weight Wi and value Vi. And we are saying the problem is to maximize the total value, ensuring that the total weight of the bag is not exceeded. Okay, so this is the problem. Now we will model this problem as integer programming problem. What we will do, we will assume a variable xi. We will assume a variable xi. What is this xi? It takes 1 and 0. So it is a binary variable. It can either take a value of 1 or a value of 0. So it will take value 1 if ith item is picked. Ith item is picked and 0 otherwise. Okay. So if item I is picked, that xi will take 1, and if xi is not picked, sorry, item I is not picked, then it will take value 0. So this variable is an indicator variable. It indicates whether item I has been picked or not. Okay. So if we write it as a mathematical model, how will that mathematical model look? Let us write it first. Okay. So what is our variable xi? It takes two values 0 and 1 if ith item is picked. Okay, and 0 otherwise. So what is the total value he is getting? So the objective function which he wants to maximize will be given as w1 x1 plus w2 x2 plus dot 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 wn xn, right? So if first item is picked, x1 will be 1, sorry, not w1 v1. So please correct me if I am doing wrong. Huh? So it's not w1 v1, because v1 is the value of the item. So v1 x1 plus v2 x2 plus dot 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 vn xn. So if item 1 is picked, x1 will take value 1 and he will have a value of v1. Similarly, suppose 1, 2 and 7, these three items are picked. So v1 will be multiplied by 1, v2 will be multiplied by 1, and all 3, 4, 5 will be multiplied by 0, 7 will be multiplied by 1, and all other will be multiplied by 0. So you will only have v1 plus v2 plus v7, right? So this is the total value he is getting. So this objective function captures what is the value he is getting given the value, given the values of the variables, which variable is taking what value. Okay. So this is the objective function v1 x1 plus v2 x2 dot 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 vn xn. In short form, you can write it as summation I is equals to 1 to n vi xi. In short, you can write like this. Okay, maximize this objective function. So there are some messages I am getting. If somebody has some doubts, please ask me. Okay, I'm not able to see the messages right now. So this is the objective function. What is the constraint? Can anybody unmute himself or herself to speak up the constraint? First constraint is that these values will have to be either 0 or 1. So you have to write xi belongs to 1 or 0 for all I is equals to 1 to n. Okay, so this is actually for all. This is a symbol used for all. Right, so this is one constraint, and this symbol means belongs to. Okay. Right, so what is one more constraint to this problem?
Weight.
Weight. So we should ensure that the weight has not been exceeded. The capacity of the bag has not been exceeded. So it will be similar to this equation. So we will have w1 x1 plus w2 x2 plus dot 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 wn xn is less than equals to capital W, right? This ensures that the bag's weight is not exceeded. And in short, you can write this as summation I is equals to 1 to n, wi xi is less than equals to capital W, right? So this is the knapsack problem. It's very simple. What are you trying to do? You are trying to maximize the value, or you can say reward. You are trying to maximize the reward such that the capacity of the bag is not exceeded, right? So this is the problem. And this we have written is as an integer programming problem, IP. Why integer programming problem? You see, all the variables which you have are integers. That is why this is known as an integer programming problem. Okay. So I have given one example problem here. A knapsack has a capacity of 15 units and there are 4 items with W1 as 5, and instead of reward or value I have written utility. It means the same thing, either reward, value, utility, it means the same thing. Utility of 3, item 2 has value 3 and weight 4, and so on and so forth. The objective is to maximize the utility without exceeding the capacity of the bag. Okay. So this is the problem statement. How are we going to solve this problem? So how will you solve this problem? If so, suppose you are going in a trekking trip. So in some mountain you are going for a trekking and you have a bag to carry. You cannot carry a lot of weight at your bag, right? If you carry weight, you will not be able to trek very high. So you have this problem, same problem. So you have some water bottles, some foods, some maybe a compass and watch, and so on and so forth. You have some items over in your table and you're deciding which item you should keep in your bag, because each item has some utility. Water has higher utility as compared to a compass. Food has higher utility as compared to suppose socks, and so on and so forth. So this is the same problem you are solving when you are going for a trek and deciding what items to pack in your bag, because the bag also has a capacity and you cannot carry more than that capacity. Okay. So how will you solve this problem, or what kind of approach you will take to decide the solution for this problem? One approach can be a greedy approach. Okay. So this is the first approach, greedy approach. So we will decide we will discuss two greedy approaches. First approach is pick the item with the highest utility. So over here, the highest utility item is 7. So highest utility item is 3. So I'll pick item 3. Now I have a capacity of 15. This has a capacity, this takes weight 5. The remaining capacity is 10, right? So the next utility item is item 1. So you can then pick item 1. Now the remaining capacity is 10 minus 5, which is 5, right? Now you pick item 2. Then you pick item 2. Item 2 has a weight of 4, so remaining capacity is 1. Remaining item exceeds the capacity, you cannot pick more items, so you just have picked item 1, 2 and 3. So using this approach, you have picked item 1, 2 and 3. Okay, so this is one approach, pick the item with the highest utility. Now suppose there was another item, or maybe, okay, we will not discuss further in this approach. There is one more approach to this problem. So this was just picking items with the highest utility. There is one more better approach to do this. What is the better approach? You find utility per unit weight. What you do, you say for item 1, if I pick item 1, I will get a utility per unit weight of 3 by 5. That is, for each unit of weight, I am getting a utility of 3 by 5 for item 1. For item 2, I am getting a utility of 3 by 4. For item 3, I am getting a utility of 7 by 5 for each item of item 3. And for item 4, I am getting a utility of 2 by 3. Right? Is it okay? So this becomes 0.6, this becomes 0.75, this becomes 1.2, and this becomes 0.66. Right? Now what you do, you pick the item with the highest this quantity, utility per unit weight. So you see earlier, item 1 and item 2 had the same utility. You could have either picked item 1 or item 2. It doesn't matter to you because both had the utility of 3. Now you see item 2 looks more looks better, right? Because it has a more utility per unit weight, because it gives a utility of 3 but only captures the capacity of 4. So item 2 is better than item 1, right? So this is another approach. Pick the item with the highest utility per unit weight. So according to this approach, you pick item 3 first, then item 2, and then item 4. And your weight will be exceeded. So this addition becomes 7 and 12. You have a capacity of 3 remaining. So according to this approach, what is your utility? Total utility you have 12. 3 plus 7 plus 2. According to this approach, you had a total utility of 7 plus 3 plus 3, 13. You see, both gives a different answer. This is better here as compared to this, right? Since this is a small problem, you are seeing this difference. Suppose there were more items, you would have actually seen that this approach is better than this approach, because you see in this approach you have a remaining weight of 3. 3 is the weight which is remaining. Just a minute. And according to this approach, you only have a remaining weight of unit 1. So if there are more items, suppose there is one more item with a weight of 3 and some utility, suppose 2 or 3, something like that, you could have picked that item as well, and the utility which have been more than what this approach gives. So I'm saying for knapsack problem, the utility per unit weight, that greedy algorithm, this is also a greedy algorithm, that works better. It has been shown to work better. Okay, theoretically it has been shown to work better. Okay, so Atul, you have some doubt.
Sir, in my voice is audible to you?
Yes, you are audible.
Sir, in method 2, we should select item 3 because its utility value is 1.2, right?
Yes, utility per unit weight.
Yeah, 1.2.
Yes.
Then after 1.2, 0.75 is item 2 will be selected. Selected
Oh,
item 1.
right, right. So it is item 2.
Yes, sir.
Thank you. Hmm.
Okay, thank you, sir.
Okay, I have done the same thing. I have calculated the ratio, and then I have picked items from there. So it is not 1.2, it is 1.4. So this is 1.4. Okay. So this is the knapsack problem, and this is the greedy approach. Okay, I hope you have understood. The greedy approach provides a feasible solution. It always provides a feasible solution. Why? So Atul, your hands is still up. If you have no more doubt, you can just keep your hand down. Okay. So this provides a feasible solution. Why feasible solution? Because the weight of the bag is not exceeded. We are always ensuring that the weight of the bag is not exceeded. Okay, but will not guarantee an optimal one. It doesn't guarantee optimal solution. Just a minute, Rajay. Example, so we will see one limitation of this approach. What approach? This ratio approach. We will see one limitation of this approach. But the approach of using that ratio, utility per unit weight, has been shown to give good solution, good feasible solution. Yet it is not an optimal one. And that will be shown by one example I have taken, where you will see that utility per unit weight may give infeasible solution. Okay, over here also you can see for this example that ratio method is giving us a utility of 12 instead of 13. Okay, so there is some issue with this approach, but still it gives good solution, and that is why this is a heuristic and not a it doesn't give an optimal, it may not give an optimal solution. This is why it is known as a heuristic. Okay, so Ajay, you are raising your hand.
Hi, very good evening, Shubham. I need to understand what sort of the model you are just talking. It is a flat. If you see, it is a water and the food, and I think I am going for the tracking where people are looking, and it is a we are consuming time to time. Then this model, we are just kind of linear model where if you see, we are considering till the we will reach to the milestone, we will carry the same weight.
So the problem which you are talking about, we are not talking about that problem. This decision is only made when packing your bag. It is not taking into account that item will be over when you reach somewhere. So that example of um, that thief is more appropriate here.
My viewpoint, at the beginning, I think at the, we will have the same problem. But slowly, if I'm planning to consume water or maybe food, then how people are just going to manage,
So
or how
the
people are just
problem
going
which
to.
you are talking about is not a knapsack problem. So you are saying that your item will reduce in weight as you move forward, right? So it becomes a different
Yeah.
problem, a complex problem as
Okay.
compared to a knapsack problem. It is an advanced
Okay.
problem of this problem. The basic idea is
Sure.
same, right?
Okay. Okay.
Okay. So limitation. So we have seen that this approach only focuses on local utility. It only focuses on maximizing that ratio. Therefore, it may give you a suboptimal solution. That is the limitation of this approach. Okay. So there is an alternate approach to this, which is a dynamic programming approach. This is an exact method. Okay. So this is not an heuristic. This is an exact method to solve this problem. Using dynamic programming, you are guaranteed to get an optimal solution. But again, this approach also has a limitation. What is the limitation? Since it is an exact method, if the problem becomes large, suppose n is 1000 items, then this method is slow. The greedy approach is very fast. It is actually very fast. It is just picking the item one at a time and then constructing the solution. Dynamic programming works a little bit differently and it takes more time as compared to this heuristic. So you see, whenever you're trying to solve a problem, you have to understand the limitations of the method you are using. You may use some approach depending upon the feasibility you have. So if you have a lot of time to solve that problem, suppose it is a design problem, so you will use a dynamic programming approach and not this greedy approach. Or maybe if it is a operational problem where you have to take decisions second by second, minute by minute, then you will not be able to use dynamic programming. So that decision is up to you, which method you want to use. Where is the trade-off? Are you willing to trade off time with accuracy or not? So that trade-off you have to decide and then come upon a solution approach. Okay. So if you use dynamic programming, you are guaranteed to get an optimal solution. Why? Because it is an exact method, but the time it takes to solve that problem will become large. Okay. So this example I have given, you go through this example after this workshop, you will be able to understand this example. Okay. So we have covered greedy approach for traveling salesman problem. So whatever we had did not discuss yesterday has been covered today. Okay. So we'll move for today's content. So we will not go through this content table today because you will not be able to understand. We will go through this table the day next day, tomorrow. Okay. So representation in optimization, you see, when we are communicating with computers, we have to devise ways to communicate with computers. So over here, we are talking about how to represent solutions such that we can feed it to a computer and do some task. Okay, so that is meant by representation. How do you represent a solution? So when I say pick item, so in a knapsack problem, I'm saying pick item 4, 5, and 7. So how will you communicate this to a computer? What is the representation you are going to use? So that is why solution representation becomes important. How solutions are encoded for optimization? What is the encoding you are using? How are you representing a solution? So there are many ways to represent a solution. I have discussed 4 ways to represent a solution, and it depends upon problem. So depending upon problem to problem, you may use one representation or the other. Okay, it depends upon problem, which problem you are tackling. So first is binary representation. So what does it mean? You have a vector. In binary representation, you have a vector, and each variable in that vector can either take 0 or 1. So this can either take 0 or 1. Okay. So it is like this. This is a binary representation. You have a vector of binary values. Where this can be useful, you see, for a knapsack problem, this representation is useful. You can say that I have n items and the index or the variable at nth position or ith position is the ith item value. So this represents first item, this represents second item, this represents third item, and so on and so forth. So this represents nth item. And this solution says that 0th item is not picked, first item is picked, second item is picked, third item is not picked, fourth and fifth are picked, sixth is not picked, nth is not picked. This is how you decode the representation. This is how you encode the solution. This is an encoding. All right, so I'm using some terms. This is an encoding. That is, you have encoded some information in this vector. And how you decode it? This is how you decode it. You will say first item is not picked, second item is picked, third item is not picked, and so on and so forth. Encoding and decoding. Okay. Real valued representation. So the problems which we discussed yesterday, for example, that linear programming problem, when we were saying that X represents the quantity of oil produced, X1 represents the quantity of oil 1 produced, X2 represents the quantity of oil 2 produced. So that is a real valued representation, right? X1, X2. So these are real values, real variables, right? Real valued variables. Those are real valued representation. So you can have a vector of real valued, and each variable can take real values, and therefore we will get a real valued representation. And you see, these are very problem dependent. This is applicable to linear programming problem. This I have given an example for knapsack problem. It can be some other problem as well, but you cannot use this kind of representation for knapsack problem. It is not correct. You cannot say that I am picking item 1 0, I am picking 0.5 units of item 1. You cannot do that. Okay. So the representation you are using mainly depends upon the problem you are solving. Discrete value representation. So what is this? I'll give you one more example. So what is a discrete value representation? Suppose there are some task. So task 1, task 2, task 3. There are 3 tasks, and there are 3 people, people 1, people 2, and people 3. Now what are you doing? You are assigning task 1 to people 1, person 1, task 2 to person 2, and task 3 to person 3. So what you can do is you can have a vector of 3 values, and you can say this represents task 1, this represents task 2, and this represents task 3. Whatever this task 1 index takes, that is the person it is assigned to. So over here task 1 is assigned to person 1, so it will take value 1. Task 2 is assigned to person 2, it will take value 2, and task 3 is assigned to person 3, it takes value 3. Again, so if I write like this, 3, 4, 5, 2, 1. So over here you see there are 5 tasks. Task 1, so I'll take another color maybe. So this represents task 1, this is task 2, task 3, this is task 4, and this is task 5. Task 1 is assigned to person 3, task 2 is assigned to person 4, task 3 to 5, task 4 to 2, and task 5 to 1. So this is a discrete value representation. Each value in a vector takes discrete values, right? This is a discrete number. It can take 1, 2, 3, 4, or 5. It cannot take 1.5. Discrete value representation. So we discussed binary representation, we discussed real valued representation, we discussed discrete value representation. There is something called permutation representation. So what does it mean? So you see, we have discussed about permutation representation yesterday when we are talking for a traveling salesman problem. So how did we represent a traveling salesman problem? If it is a 6-city problem, we said we will label that city as A, B, C, D, E, and F. And if I write like this, B, D, C, A, E, F, what does it mean? It means that salesman starts from city B, visits city D, visits then city C, then A, then E, then F. It is a permutation. You see, this can be changed. That permutation of cities can be changed. It can be B, A, D, E, C, F. So we are writing a permutation. And this is a way to represent a solution for a traveling salesman problem. Is that all right? You can also write traveling salesman problem as discrete value representation, right? Because there are similarities between permutation representation and discrete value representation. What is the difference? The difference is in permutation representation, the values cannot be repeated. So you cannot have 2 A's. You cannot have B, A, D, A, E, C and leave out F. In permutation representation, you cannot repeat a value again and leave out a city. You cannot do that in permutation representation. In discrete value representation, you can do that. So suppose in this example, you are assigning task 3 to city person 1 as well. So task 1 to person 1, task 2 to person 2, and task 3 to person 1. So in discrete value representation, these numbers can be repeated, but in permutation representation, these numbers cannot be repeated. And why is this helpful? Can you think about why is this helpful? It may be a lot to ask from you now, but if you can guess, then it is a good thing. Why we use permutation represent? So I'm framing the question again. why do we use permutation representation for a traveling salesman problem and not a discrete value representation? The question is, why are we using permutation representation for a traveling salesman problem and not discrete value representation? Yes, yes, you can answer, no problem.
So we can have to do this because each vertices has to be or city has to be traveled once.
Right. So what are you doing
So we
is,
cannot exclude anyone.
yes. So what are you doing is, you can actually use discrete value representation for traveling salesman problem. You can. There is no harm in it. There is a harm, but no one is stopping you to use discrete value representation. But what are you losing? You're losing a constraint.
I think it also satisfies the constraints. So the one of the constraints can be easily represented, so that way it helps us in solving the problem.
Right. So that is what I was saying. So what I'm saying is you can, so there is no restriction you have to use permutation representation for traveling salesman problem. No one is stopping you. You can use discrete value. But what are you losing? You are losing that constraint. When you are representing a solution of traveling salesman problem using permutation representation, you are involving that constraint. What is the constraint? You cannot travel a city twice. That constraint has been encoded in your representation. You don't have to worry about that constraint again. So this solution is not a feasible solution. This is not a feasible solution. And if you use discrete value representation, this solution will become feasible solution. So using permutation representation, you are actually enforcing a constraint that a city cannot be repeated again. It has to be a permutation. Okay. So you are using your representation to uh, to incorporate the constraint in your problem. So you are actually, in a way, using the representation as your constraint. The constraint becomes embedded in your representation. Is that all right? Any doubt? So while designing a problem, you have to decide what kind of representation you use. And this is no way a exhaustive list. There are many other more representation techniques you can use. It is up to you. It is just a design choice. You can take any kind of representation, and many, many more representations there are. Okay. So binary representation, we have talked about this. It is just a bit either on or off. Okay. Real valued representation mainly used in linear programming problems. It's not true. You can use it in other areas as well, but I have taken an example of linear programming problem. Discrete value representation, assignment problem. So some task has been assigned to some person. The example which I gave, task 1 to person 1, and so on and so forth. Permutation representation, a classical example is traveling salesman problem. Okay. So why is representation important? So by the way, there are some chats in the WhatsApp group. So I would request Professor Sudeep to pause me and discuss those chats. Okay. So why representation is important? Any meta-heuristics requires a way to encode a solution. We were talking about this, right? You have to communicate with the computer to do this. So representation helps you communicate a solution to the problem. Okay. The choice of representation impacts efficiency and effectiveness. So for a traveling salesman problem, if you go for discrete value representation, it reduces your efficiency or effectiveness, right? If you use a permutation combination, permutation representation, you are in a way incorporating the constraint in your problem. So the choice is important. Okay. Key characteristics. So to understand this, we have to understand neighborhoods. When we have completed neighborhood, then we'll come back to the key characteristics of representation. We will come back to this. Okay. So this we have decided, discussed, and this point also we will discuss when we have discussed neighborhoods. Okay. A well-designed representation improves search efficiency and helps find better solution faster. Direct versus indirect encoding. So previously, the examples which I gave for the binary representation, the discrete value representation, real valued representation, or the permutation representation, those were direct encoding. What does it mean? It means the decoder. So I have talked about encoder and decoder. So for a traveling salesman problem, what is a decoder? So if I go back, if this is the encoding, So what is a decoder? It just say, suppose you have to get the objective function. How will you get the objective function? You take BD. So what is the distance between BD? You add. Then what is the distance between DC? You add. Then CA, then AE, then EF. You will get the objective function. So this is how you're decoding the solution. Okay, this is my representation. This is my encoding. I can decode and then obtain the objective function. So this is a decoder. And you see, this is a very direct decoder. So whatever your solution, that representation is over here, you can quickly get the solution. So you see, this is not actually a solution. This is just a representation of solution. What is an example of indirect encoding? So for example, scheduling of task on a machine. So suppose there is machine 1, and that machine has to do some task. So suppose job 3, then he has to do job 1, then it has to do job 4, and then it has to do job 5. Okay, so these are the four, right? So it is not 5, it is job 2. So these 4 jobs this machine has to do in this order. Okay, so we can represent this order as a permutation representation. So what will be the representation? The representation will be 3, 1, 4, 2. This is a permutation representation for scheduling of task. But this is not a direct encoding. Why? Because there may be some idle time between the task. So for example, job 3 starts at 8 a.m. and ends at 12 a.m. Okay, but job 1 starts at 2 p.m. So there is a gap of 2 hours between job 3 and job 1. Now, when you write 3, 4, 2, 1, you are losing some data. You are not able to say then when is job 1 starts and when job 3 ends. You're losing some data. So you need a decoder. So from this solution, from this representation, what is the solution? When does job 3 start and when it ends? When does job 1 starts and when it ends? That information will be given by the decoder. That is the indirect encoding. So there has to be some function which takes this in as input and will give you the complete solution. It will say job 3 starts at this time, ends at this time. There is some idle time, and then job 1 starts, then job 1 ends, and there is some idle time, and so on and so forth. And when you obtain this schedule, when you obtain that the time at which it starts and there is some idle time, then only you will be able to obtain the objective function, right? So why is it true? So for example, there is one objective, make span. What is make span? Make span just means the completion time of, so I'll just use one more page maybe. So for scheduling, there is one objective. What is that objective? Objective is make span. So minimize make span. The objective is to minimize make span. What is make span? Make span is the completion time of the last job. Okay, so it means the completion time of the last job. So if you have a machine 1 and you have some jobs, and suppose the completion time of the last job is 12 units, and there are some idle time over here. So you will not be able to obtain 12 units if you don't have a decoder. If suppose you have encoded this as job 3, job 1, job 4 and job 2, suppose this is the encoding, you can just add the processing time P3 plus P1 plus P2, P4 plus P2. So it just says this is P1, processing time of P1, this is processing time of P3, this is processing time of P1, this is processing time of P4, and this is processing time of job 2. But this will not give you the make span because there are some idle time. Since there is some idle time, you have to add to this idle time after job 3 plus idle time after job 1, idle time after job 4, and idle time before job 3. So you have to add these idle times as well. When you add this idle time, then you will be able to obtain the completion time of the last job. Okay, make span. So to obtain these idle times, you have to have a decoder. So that is the idea of direct encoding and indirect encoding. We will not go into indirect encoding ever in this course. This is just for your information that you can have a direct encoder and indirect encoder. We will not use indirect encoding in this workshop. This is just for your information. The encoding does not directly represents a complete solution. Okay, this is not a complete solution. This is a representation of simplified representation of the solution. A decoder is required to generate a valid solution. Example, a sequence of tasks represents the order of execution but doesn't specify the start time. The decoder inserts idle time and ensures feasibility, considering constraints like precedence and machine eligibility. If you don't understand it, doesn't matter. Okay. So is this clear? Direct encoding and indirect encoding? Okay. So we have understood how to represent a solution. Now we will talk about objective function. So you see, what are we doing? So if you go back yesterday, we have talked about a crude algorithm. What was the crude algorithm? You evaluate the objective function of each of the solution and pick the best. And we talked about that it is not feasible to do it, right? For larger problems, it is not feasible to do it. And we said that what we will do is we will intelligently pick solutions. So Metaheuristic, what it does, it picks a solution, it obtains the objective function of that solution, and then moves to another solution which may have a improved objective function. So it moves from one solution to the other. This is how a metaheuristic works. Just a broad idea. So it will start from a solution. This is about single solution metaheuristics, not population based metaheuristic. So how does single solution metaheuristic works? It starts from a single solution. It checks some solutions around it. It moves to that solution if it has a better objective function. And then again, it checks some solution around it. It moves to another solution and so on and so forth. So at a time, it moves to a better and better and better solution. So it is evaluating objective function at that point. Okay. This objective function may be exactly the objective function of your problem, or we may use a modified objective function. I will repeat again. So when you are giving the objective function to your metaheuristics, you may directly use your objective function of the problem to guide the metaheuristics to a better solution, or you may modify that objective function appropriately and then give to the metaheuristics to solve the problem. So we will talk about why do we need to modify. Okay. So definition, the objective function is just a function which takes input as the solution and gives the output. So over here, we are only talking about one-dimensional objective function. So it is only one dimension, one objective. We are not talking about multiple objectives. Okay. So role, it guides the search towards better solution. So you need to have the idea of what is the value of the objective function. That is how you will guide the metaheuristics. You will say, okay, this seems higher, go to a lower, go to a solution with lower objective function. If you are minimizing, again, go to a solution which has a lower objective function, and then you will proceed the search. Poorly designed objective function can lead to ineffective optimization. What do I mean by poorly designed objective function? So we will see one example and then you will understand. Okay. So this is an exam scheduling problem. What is this problem? You see, when a university schedules exam, it always ensures that there is no conflict. What is conflict? So a student cannot have two courses, the exams of two courses at the same time, right? How will he give exam for the two different courses at the same time? So that is meant by conflict. So the problem is a university needs to schedule final exams while maintaining while minimizing conflict for student. I have written minimizing, but the goal is to actually make it zero. There shouldn't be any conflict. Still, I have written minimizing. Okay. So again, what is the conflict? A student cannot have two exams at the same time. So that is a conflict. So what can be the objective function of a problem? Whether there is a conflict or not. So if you give me a solution, I will check, okay, this solution has a conflict. So this is 0. So the objective function is that objective becomes 0 if there is a conflict, or 1 if there is no conflict. This is the objective function of a problem. You give me a solution S, that is, you give me a schedule for the exams, and the objective function evaluates to 1 if there is no conflict, and it evaluates to 0 if there is a conflict. So higher the objective function, the better it is. It means if the objective function takes value 1, then that solution I'm looking for. If the objective function takes value 0, I'm not looking for that solution. Okay, so this is initial objective function, because that is what I'm looking for. I'm looking for a solution which doesn't have any conflict. So initially, when I modeled that problem, I modeled it using this objective function. Okay, this is the objective function, but there is some issue with this objective function. Before asking the issue, have you understood the objective function? Right? I assume that you have understood the objective function. It just says if a solution has no conflict, that objective function will take value 1. If it has a conflict, then it becomes 0. Okay. There is an issue with this objective function, this kind of objective function. This objective function doesn't differentiate between two solutions with one conflict and 100 conflicts. Whether the solution has one conflict or the solution has 100 conflicts, it will give you 0, because there is a conflict. And the search will lack guidance to improve the, so to move to a better solution, it will not understand. It will say, okay, this is also a bad solution, this is also a bad solution, this is also a bad solution. It will not be able to distinguish, this is somewhat bad, this is very, very bad, this is not so bad, and so on and so forth. It will not be able to distinguish. So you need to modify this objective function in a way that you can guide the search towards a better solution. What is an improved guiding objective function? You take an objective function f dashed, so I should have written as f dashed. What is this objective function? It sums the number of conflicts. So it will say, suppose there are 100 conflicts, but it evaluates to 100. If there are one conflict, this sum will evaluate to 1. Now what we are looking for? We are looking for a solution which evaluates to 0. Okay. And now if you have a solution with 100 conflicts and there is a solution with 9 conflicts, you can say, okay, this 9 conflict solution looks better. Move from this 100 conflict solution to a solution where there are 9 conflicts. And from there you can move to a solution where there are 4 conflicts. And from there maybe 2 conflicts, then 1 conflict, then 0 conflict. So you can guide the search using this objective function, not the previous objective function. So this is what I mean by guiding objective function. You may need to modify your objective function to better or improve the search process. Is it all right? So what is a self-sufficient objective function? So for example, the traveling salesman problem. So if you have a solution, you can just add the distance of each of the cities, right? So from A to B, B to C, you can just add, and whatever that distance is, you can take that as objective function. And if you have another solution with a reduced total distance, you can just move to that objective function. So in a traveling salesman problem, there is no need to modify the objective function. But for some problems, you may have to improve or modify your objective function. So that is the idea. Okay. Right. So we have talked about solutions. Yes, Ajay.
Sorry, is related to the same problem, is a travel wala. अगर वहाँ पे bridge टूटा हुआ है, where if you see in the statement we have written he has to go to all the places, so it will consider as a constraint or
So
conflict in terms. Sorry, it will consider as a conflict while deciding the objectives.
No. So what will happen is, so suppose what I will do is I'll take one blank page, and suppose there is these cities.
Yeah.
Right, and these are connected in this way. So this is connected to this. I'll just connect it and then we'll talk. Okay. So this is how they are connected. Okay. Now what are we trying to do? You are saying that suppose there is no connection between, there is a bridge which is broken between city, so A, B, C,
yeah,
D, E, F, G and H. So when you are saying suppose there is a bridge which is broken between H and E, so what you will do is you will remove this connection. You will say that there is no connection between H and E.
Okay, but initially जब मैंने उसको decide किया था as a part of objective, तो मैंने ये बोला कि postman has to cover all the points. अब उसके बाद later on it is a kind of constraint. I will just remove or I will consider as a conflict in terms of the objectives.
So when you are solving that problem, you have to check whether the distance you are mentioning is appropriate or not, whether there is a
Okay.
connection between the two cities or not before starting, right?
Okay.
Why will you
Okay.
consider a connection where there is no connection?
Okay.
Okay.
Okay. Okay. Thank you.
Right. So where were we? We were saying that we have a way to encode a solution. We have a way to get the objectives, but there are constraints as well, right? So some problems have different kinds of constraints. How to handle constraints? So for example, when we are talking about knapsack problem, I told you that we can represent a knapsack problem as a binary vector. Now suppose you have a solution 1 1 1 1 1 1, and the total weight of this solution becomes 60, but the bag which you have has a capacity of, so capital W capacity becomes, suppose it is 50. So this solution is actually not a feasible solution, and your encoding doesn't have a way to distinguish between a feasible solution and an infeasible solution, right? It is just an encoding. You are not saying that this encoding ऐसे ही work करेगा. You are just saying it is an encoding and it is a binary encoding. Each can take either 0 or 1, and that is what it is taking. Each of these are taking 1. So your encoding doesn't have an issue, but there is a constraint you have to handle. What is the constraint? That the capacity of the bag cannot be exceeded. How will you handle those kind of constraints? And it is important to handle constraints because you are not here to find a solution which is infeasible. You are here to find a solution which is feasible. It satisfies all your constraints, right? So there are strategies to handle constraints. And mind you, this is a very tricky thing to work with. If you have constraints, you have to be clever on handling constraints. If your problem is a very, very constrained problem, finding one feasible solution becomes difficult. Okay. For example, there are problems where it doesn't have an objective function. It just says find a feasible solution. Over there, you don't know how to start the search because you don't have a feasible solution to start with. So remember, we are talking about metaheuristics, and we say that it starts with a solution and then finds another solution and which is better and then moves to that solution. But suppose there is a problem where it is very difficult to find, or the problem is to find a feasible solution. We are just saying ki find a feasible solution. For example, that I'll not give an example right now because it becomes confusing. So there are problems where there is no objective function. It just says find a feasible solution. And in that case, finding a feasible solution becomes difficult. So those problems have different ways of handling it. We are here to see how to handle constraints. Okay. So one solution is reject strategy. You say that if we encounter a solution which is not feasible, we'll just reject the solution. We will say, okay, it doesn't bother about the solution, move with some other solution, search for some other solution. You again find a solution and you see, okay, this is also not feasible, reject that solution. Okay, this is one strategy. This strategy has a limitation. What is that limitation? If your problem is a very constrained problem, you will just waste your time finding solution and rejecting them. You'll just find a solution, reject them, find a solution, reject them, find a solution, reject them. You're wasting your efforts, you're wasting computational efforts. Okay. This is not a very good strategy. It works when your problem is not very constrained, but you are losing efforts, right? Penalizing strategy. This is another form of strategy where what you do is in the objective function. So I'll write like this. So suppose this is the objective function f of s. What you will add is you will add a penalty. So suppose there are some constraints, constraint 1, constraint 2, constraint 3, constraint 4. So what you will do is you will say alpha I times constraint 1 violation. So if constraint 1 is violated, there is a penalty of alpha I. So I'll write in a better way maybe. What I will do is I will write like this. So so constraint 1 is a plus b, or maybe w1 x1 plus w2 x2 is less than equals to c1, w3 x1 plus w4 x2 is less than equals to c2. Suppose there are two constraints and I'm writing this constraint as w1 x1 plus w2 x2 is minus c1 is less than equals to 0, and this constraint as w3 x 1 plus W4 x2 minus C2 is less than equals to 0. The same thing, I'm just bringing C1 to this side. And this constraint is H1 and this constraint is H2. So what I will write is, I will write alpha 1 H1 plus alpha 2 H2. It says that if H1 is violated, add a penalty alpha 1. If H2 is violated, add a penalty alpha 2. Now you see, you are not using the original objective function for the search. You are using this modified objective function. And a higher value of, if it is a minimization problem, a higher value of objective function indicates that some of your constraints are violated. A lower value of objective function indicates that maybe none of your solutions are violated. None of your constraints are violated. So this is another strategy. You remove these constraints from the problem, you add a penalty to that objective function. You use the modified objective function. I guess you will not be able to understand it clearly how it is working, but I'm giving you the overall idea. We will not use this in our workshop. These are all ideas of handling constraints. What we will do, so for the knapsack problem, we will say, I will come to that question. For the knapsack problem, we will say we will remove the capacity constraint. Remove the capacity constraint, all solution works, but the objective function will not be the original objective function. I will have that plus penalty of violation. If it violates by 1 unit times alpha 1 will be the penalty. If it violates by 2 units, 2 units times the violation will be the penalty. If it violates by x units, that x units times the penalty is the violation. So we are weighting the violation and then adding it to the objective function. So the more violation is there, more worse is my objective function. Less violation is there, less worse is my objective function. And we will guide the search using that. Okay, so we will just remove this constraint and add a penalty to the objective function. This is penalizing strategy. There was one hand up. Yes, please speak up.
Okay, so my query was like last someone mentioned that if there is bridges connecting the edges and one bridge has been has broke down. So in that case, we can assign the utility of that bridge to be infinity also,
Yes,
or
the
some
distance is
different
infinity.
thousand.
You can just
So
say
we
that
don't have to
distance.
modify the objective also.
So you can just say the distance between f and h is infinity. You can say that as well. Instead of that, you can just say there is no connection between f and h.
So under these two circumstances, like modifying the objective function and not modifying the objective function, but we are assigning a different value to the state of that node. So is there any particular difference in these two scenarios?
No. So what you see, what you are saying is absolutely correct. When we work with mathematics, so when we say this is edge A to G, this is edge A to B. So the weight of this edge, distance of this edge is DAB. The distance of this edge is DAG, and so on and so forth. So when I write the mathematical formulation for traveling salesman problem, I will just add D I to J, I comma J belongs to all the edges. Now, if there is no edge between, suppose A and E, there are no edge, right? So I will assign that value to infinity. So DAE will become infinity. So this is how I add it to my objective function, and the solution will not take that edge. That means that there is no edge. We are adding all the edges, but if that edge value, so that distance is infinity, the solution will not take that edge. So both are same thing. If there is no edge, you see, we are talking about two different kinds of models. In network models, you don't need infinity. You just remove that edge and you can work with that. You can just say that there is no edge between A and E. But if you work with mathematical model, how will you say that there is no edge between A and E? You can just say that the distance between A and E is infinity. These are different models, modeling choices, right? These are ways to model the problem. Is that all right?
Yes, perfectly. We can also assign a higher number also, like
Yes,
10,000 or
infinity doesn't work in mathematics. You can have a very high number. I just used infinity to clarify the doubt. You can take 1 million or so, or something like that. Okay. Okay, so another strategy is repairing strategy. So what is repairing strategy? So for this, I have taken one example for the knapsack problem. Okay, I will just show you the example. You can read the PPT later. If you have doubt, you can ask me in the next class. So what is repair strategy? So suppose this is the solution I have obtained. 1 1 1 1 1 1 and 1. Suppose this is the solution I have, and this weight comes out to be 60 and my capacity is 50. So what I will say is, instead of rejecting this solution, in the reject strategy, repair the solution. You have spent time and effort to obtain this solution, right? Why will you reject this solution? You have a solution, you just repair it. How will we repair it? It depends upon problem. So it is problem specific. Some problem have different kind of repair strategy, some problem may have different kind of repair strategy. What we will do here is, we will again obtain that utility per unit weight, and we will say remove the object which has the least utility per unit weight. So suppose this object has the least utility per unit weight, make it 0. Now again check what is the total weight. Suppose the total weight becomes 55 and you have a capacity of 50, you have to remove more. So again, out of the ones which are there, remove the one which has the least this ratio. So suppose this is the one, you make it 0, and now the weight comes out to be 49 and it is under 50, so your solution has been repaired. So this is a repair strategy. Okay, decoding strategy. So what does it mean? You see, you are in a way um, using a representation which doesn't allow um, um, a violation of constraints, and then you are using a decoder to decode the solution. So that is what it means by decoding strategy. So for example, in traveling salesman problem, that representation itself has a constraint, that permutation representation, and it doesn't allow for infeasible solutions, because we are using permutation combination, permutation representation. And then you decode the solution. What is the decoding? The distance of each of the thing you take, and then you do it. So this is one example of decoding strategy. Okay, so this is how we handle constraints. Any problem, any doubt? Okay, so we will take 5 minutes break. So we will meet at 6:40, maybe 42. Mark your attendance now, because we have a lot of things to discuss. Just a minute, we have a lot of things to discuss, and I don't want to spend time again. So I'll give the code. Uh, Professor Sudeep, are you here?
Yes, I shall share the link.
So please enable them to mark the attendance. We will start at 7:43 maybe PM. Okay. Yeah, there was a doubt. Yes, you can ask.
okay. Can you give an example of like indirect and direct decoding real life application?
That
Indirect and
scheduling problem. So where you are just representing the solution as a permutation. So you have um, suppose 10 jobs. So 7 6 4 dot dot dot. Maybe this is one permutation, but this doesn't capture the start time of all the jobs and end time of all the jobs. Right? It is just saying the sequence. This is how you process the jobs. So you need to have some function which will give you the start, given this input. So given this sequence as input, that function will tell you, okay, job 4 starts at 4 p.m., job 5 starts at 6 p.m., and so on and so forth. So you need a decoder to take the representation as input and give you the exact solution to the problem.
thank you, Shubham. That was really
So,
understandable.
so please mark the attendance. We will start at 7:43. Okay. Sorry, not 7666. Sorry, 6:43. Please put your hands down. Huh? Okay, so we will start now. So yeah. Okay, so there are no questions in the WhatsApp group. I'll start. So this is a very important concept, state space landscape, and may be confusing. So please bear with me. I'll try to make it simple. Okay, but it is an important concept to understand. What is it? So you see, yeah. So so if you have a function, so we are talking about a one-dimensional objective function where we have only one objective, right? So suppose there is one variable, only one variable. So the problem is of one variable, one objective function, and that is x1 or maybe just x because we have only one value, and this is y. Y is the objective function, or instead of y, I can write f of x, right? So you see, you can plot the objective function with respect to the value of x. Now, by the way, uh, we are actually going towards the discussion of single solution metaheuristics. Okay, so I'll just take some ideas from there. Now, what we're talking, we are saying that metaheuristic will start from one initial solution. Okay, so suppose it starts from this solution. This point it starts with x1, and it is a minimization problem. Now, if it is a minimization problem, it will try to move to a solution which has a better objective function, that is a lower objective function than its current solution. So what is the idea? It checks its neighbor. So over here, suppose this x1 is, suppose x1 is 3.5, and you have to decide what is the what range you will consider as neighborhood. So suppose you are saying 0.1 distance in the right and 0.1 distance in the left, that area I'll consider as neighborhood. So what you will do, you will take two values. You cannot take the whole range, you have to take individual values. So you will take 3.6 as one value and 3.4 as one value. You will have this solution as one and this solution as one. You will compare the objective function value at 3.5 with 3.6 and 3.4. And what you will notice over here is, okay, 3.4 has a lower objective function that then x is equals to 3.5. We will move to x is equals to 3.4. Again, you will take the neighborhood, you take 2 points, and then you move to this point, this point, this point, this point, this point, and you come over here. Similarly, if you start, suppose over here, if your starting solution is this one, initial solution, you will come actually to this point and you will not be able to come to this global optimal. Or suppose if you start from here, you will come over here and then you will be stuck over here. Okay, so that is not what I'm pointing out. The thing to realize is this function which I have plotted over here, this function, this is what is known as the landscape of the problem. Okay, this is known as the landscape of a problem. State space landscape. So this is the state space or the solution space, and according to this, your landscape takes the form, right? Depending upon the state space, the solution space, your landscape forms. Why am I focusing on this? You will understand when I move forward. Okay, just realize the thing is, this landscape is important. This landscape is important. If there is a way, if there is, so suppose over here there are many local optimas. These are local optimas, right? These are local optimas. If there is a way to modify this landscape and suppose make it like this, if there is a way to modify this landscape and make, instead of multiple local optimas, to one global optima, and then start the local search, then you start at any point, you will come to this point, right? So we will try to do something like that. We will try to modify the landscape of the problem. If your landscape is very rugged, if it is multimodal, it means there are multiple maximas and minimas. There are multiple maximas and minimas, then it is a difficult problem to solve. That metaheuristic will struggle to solve that problem. If you can modify the landscape in some way or the other, we will see how we can modify the landscape. Then the efficiency of the metaheuristics increases many folds. Okay, so that is the idea. And when you are actually implementing a meta heuristics, it is actually a difficult thing to understand how the landscape is. Why? Because to plot the landscape, you have to obtain the objective function value at each of the points, each of the x points. And if you're doing that, you can just pick the value which is best. Why are you worrying about modifying the landscape? If you're plotting the function for each of the x points, point of x, and then only you will know. So at each x point you will obtain what is the objective function at each x point, and then you will plot the objective function, right? So if you're doing so, why not just pick the best solution? We have seen that that is a bad approach. That is a bad approach. So how do we understand how the landscape is? So actually a lot of research has been done, and for problem types, so suppose for traveling salesman problem, for some kind of scheduling, single machine scheduling problem, the landscapes are already been studied, and they know how to produce a good landscape, what approach to take to get a good landscape. These studies has already been done. Okay, so when you are designing a meta heuristics, you have to go to the literature and see what, I will use a term operator, what operator to use to get the neighbors. We will discuss what are these, what operators to use to get a neighbor, such that my landscape becomes simple, it is not rugged. Okay, so yeah, just give me a minute. So when you are designing your meta heuristics, you have to go to the literature and see what operators are better, such that your landscape becomes less rugged. Okay, I know it will not make a lot of sense right now, but as we proceed you will understand what I am saying. So the conclusion is, the idea is, you will not be able to tell how the landscape looks. You have to go to the literature and see, okay, if we use this kind of approach, then the landscapes become better. We will use that approach and we will get a good solution. That is the idea. Yeah, there is one hand up.
Sir, actually, how do you define the landscape when the x-axis can go to infinity? So when to stop, till what range, and think that this is the landscape range.
So if we are talking about an optimization problem, and if it is a, so I will again use a term, bounded feasible region. What does it mean? It means that your feasible space is not infinity. So we generally work with such problems where the feasible space is not infinity. If it is infinity, there are ways to handle those case also. But for example, traveling salesman problem, you can count the number of feasible solutions because it is just a permutation. So if it is a 20 city problem, you know that the permutation will not be 20 minus 1 factorial by 2. These are the many number of solutions traveling salesman problem can have. Obviously, you cannot enumerate this number of solutions, but you know that it is bounded. It cannot be more than this. So that will not grow high. So, and but a better question to ask is, I will come to your if you have understood or not, but a better question to ask is, I have taken a real valued x and given this landscape. We can define a neighborhood very easily for a real valued number. We are saying that it starts from 3.5, we will go to 3.4 and 3.6, right? But what happens? How will we define a neighborhood for a traveling salesman problem? We have suppose one permutation. What is the neighborhood permutation? How will we go to a neighbor? How will we define the next point? That is a good question to ask, and we will see how we define it. And that actually governs. So how to move to a next neighbor? What will be a next neighbor? Those decisions when taken defines the landscape. You can have different kinds of neighbors. We will see. I may confuse you now, but we will see. And that governs the landscape, how your landscape will look. Before that, did I answer your question?
Yeah, thank you.
Okay. Yeah, so features of the landscape, there can be local optima. So these are local optimas. This is also global optima, is also local optima. Global optima and plateau. So you can also have plateau. Okay, so what does mean? It is like this, something like this. Okay, plateaus. This can be curves as well. Okay. Understanding the landscapes helps in designing algorithms to navigate the search space effectively. So we should have an idea about the landscape. Okay, it is a difficult task to do, by the way. Optimization algorithm aims to avoid being trapped in local optima and strive to find the global optima. Yeah, just generic comments. Neighborhood in optimization. So let me see how much I am yet to cover. So I guess neighborhood fitness initial solution local search. Yeah, I can cover in 7:30. Okay, so neighborhood, a set of solutions that can be reached from a given solution by making small modifications. So if you are at a solution, whether it doesn't matter for a real valued solution or traveling salesman solution, traveling salesman problem solution, if you are at a solution and you can reach to a neighborhood solution with some change in the current solution, then that solution can be labeled as a neighbor of that solution. Key characteristics define the scope of exploration. This is an important term. We will discuss about this for local search algorithm. Neighboring solutions are typically similar to the current solution. So examples of neighborhoods. For traveling salesman problem, we can swap two cities, reverse the sequence of two cities. Just let us see some examples. So suppose we have a permutation of A, B, C, D, E, F, G, H, I, J. So this is a 10 city problem and this is solution 1. So suppose you are at this solution and you are trying to find a neighbor of this solution. So there are many ways to modify a permutation solution. First is insertion. Whether it is a good neighborhood operator or not, that is a different question. Here I am telling you how can you produce a neighbor. Whether it is a good operator or not, we will discuss. We will not discuss it. We will leave that for now. But we are just talking about how to create a neighbor. So this is one solution. What is insertion? You just pick a city and just insert it in some other position. So that is a neighbor. A, B, I, C, D, E, F, G, H, J. This is one neighbor. Let me put it here. Second is swap. What is swap? You take two cities and just swap, or maybe not neighbor cities. I suppose this city and this city. You just swap. So it will be A, B, C, D, E, and then I, G, H, F, J. This is again a neighbor. The third is inversion or two-opt or inversion. What is this? You take two cities. So suppose you are taking city B and city I. You take two cities and reverse the order. So it will become A, I, H, G, F, E, D, C, B, J. So you are reversing the order of these cities. It is known as two-opt or inversion. There are many ways to do it. Okay, these are operators of creating a neighbor. Operators of creating a neighbor. Now, you must use only one operator to create a neighborhood. So if you are at this solution, you must use one. So you have to choose one. So suppose we are choosing two-opt. And by the way, since we are at a traveling salesman problem, two-opt gives a good value. It gives a good value. These insertion swap have a very rugged landscape. I'll show you what I mean. I cannot show you, I'll just discuss what it means. So suppose we are talking about two-opt. We are at this solution, solution 1. All the solutions you can reach with one two-opt. That is, you can take B and I and then reverse. You can take C and I and then reverse. You can take E and G and then reverse. All solutions you can reach with one two-opt operator. Take any city, any two cities, I and J, or maybe I and B, H and E, any two cities, do the two-opt. Whichever solution you can reach by one two-opt will become the neighbor of this solution. Okay. Now you see, this is distance 1. So we have an idea of distance. Earlier when we were talking about real valued, the distance was 0.1 unit. Over here also the distance is in terms of two-opt, one two-opt. Similarly, if you are talking about swap neighborhood, you are at solution 1. All the solutions you can reach with one swap will become the neighbor. neighborhood. Will create the neighborhood. So you take city B and city I and then swap. City D and city D and G and the swap. All the neighbors you can reach with one swap. Only one swap will be the neighbor. All the cities you can, all the solutions you can reach with one insertion will be a neighbor. So this is an example of a neighborhood. So I am creating a neighborhood. I'm creating a neighborhood with one, so suppose 1 2 opt. Okay. This is a neighborhood. You can, so the idea of neighborhood is clear, by the way, or maybe one swap, or maybe one insertion. That is the neighborhood. You can enlarge the neighborhood. You can say, okay, I will enlarge my neighborhood. My neighborhood will be either one opt, sorry, either 1 2 opt. What am I writing? 1 2 opt operator or 2 2 opt operator. So all the solutions I can reach with either 1 2 opt or 2 2 opt. That is, I will do two or maybe one swap or two swap. So all the solutions from this solution I can reach by either doing one swap or two swap will be my neighborhood. You're enlarging your neighborhood. So if you enlarge your neighborhood, computation times increases. So suppose you are saying not 1 2, you are saying all swaps. So if you say all swaps, you are actually searching the whole search space. All swap means all the solutions you can reach from this solution. It doesn't matter one swap, two swap, or three swap. N number of swaps. All the solutions you can reach with n number of swaps. So the larger your neighborhood becomes, the more difficult it becomes to search that neighborhood. Okay, so the definition of neighborhood you have to decide how large you want your neighborhood to be. Yes, Charles.
Is just that it is appearing that swap and 2 opt are just the same.
No, swap and 2 opt is not same. So you see, swap only changes the position of B and I. So over here, what I have taken I and F. So I'm just changing I and F. H and G remains same. So when I and F changed, G and H position did not change. When I'm doing 2 opt, it is getting reversed. F comes here, I comes here, H will come here, and G will go there. Right? Swap is just taking two cities and interchanging the position of those two cities. But 2 opt is reversing the order of all the cities in between. Is that all right? Okay.
Just please give one example from the please.
I can give one example. So suppose over here the inversion is, when I have done inversion or 2 opt for this, when considering B and I, this is the neighbor. But when I do swap of B and I, the solution will be A, I, C, D, E, F, G, H, B, J. You see, this is swap of city B and I. What is this? This is 2 opt of city B and I, right? So 2 opt solution neighbor is different from swap neighbor. Is that all right?
Okay. So choosing any 2 points and then reversing the order for all the entities between those 2 points.
Yes. So you will better understand this when you do it in a graph. I don't know if I will be able to do it correctly or not, but you can take an so A, B, C, D, E, F, G. So first my solution is A, B, C, D, E, F, G. Okay. So initially this is my solution. Okay. Now when I do swap, so what my solution will be A, B, C. So suppose I am swapping B and E. So A, E, C, D. So this is swap. A, B, E, D, A, E, C, B, A, E, C, D, B, F, G. And 2 opt will be A, E, D, C, B, G. So we are taking this city and this city. So first this is swap and this is 2-opt, right? So when you do it in the diagram, you will understand. So this is this solution. What is 2-opt solution? You see 2-opt solution is A, E, D, E, D, this, this, from B it will go to this way. So what 2-opt is doing, it is removing two of the edges. It is removing two of the edges. Okay, I have removed F. Just a minute. Here will be F and G. So what 2-opt is doing? What 2-opt is doing is it is removing the edge AB and EF and interchanging the edges. But what swap will do, you go home and try, it will do a different thing. Okay, so that is the idea. 2-opt is actually preserving what I will say, relative position of the you go and try, you will understand. Okay, yeah, Advitya.
Sir, am I audible?
Yes, you are audible. And please don't call me sir, you can call me Shubham.
Okay, okay, sorry. So, sir, I just want to know, like, for to opt inverse, like this process, like if we have to do like opting for two times, so is it consecutively, like firstly we have done one to opt, then again we have to do one to opt like this?
So you see, I have given 2-opt as an example. So what you are doing is you are performing one 2-opt, another 2-opt. Okay.
Okay.
So there are other ways also. There is something called 3-opt. If you go and study, you will understand what are these. But just to give an idea, I have listed down few. There are 3-opt also, 4-opt, N-opt also. There are more such kind of neighbors. Okay. There were one
And
more.
like
Yeah.
one more doubt I have, like how to know up to what we need to enlarge our landscape. Uh, that-
Okay, so enlarging landscape, it becomes, so there is one idea of, there is one heuristic which is known as variable neighborhood descent or variable neighborhood search. There are two different, these are two different meta heuristics. One is variable neighborhood search and one is variable neighborhood descent. The idea is there are different kinds of neighborhoods. There is one neighborhood which will perform one kind of operator. There is another neighborhood which will perform different kind of operator. So you move from one neighborhood, search that neighborhood. If you don't find a good solution, move to the second kind of neighborhood. If you don't find another good solution, you move to the third kind of neighborhood. And in such cases, we try to keep smaller neighborhood first, then bigger neighborhood, then more bigger neighborhood, and so on and so forth. So that is variable neighborhood descent. This is what is variable neighborhood descent. There is a stochastic version of that which is known as variable neighborhood search, VNS, VND and VNS. Those are different kinds of meta heuristic. All are based on local search.
Okay, okay. Thank you so much.
Any questions? Any more questions? Yeah. Please speak up. I saw a hand and I am not able to hear anything. Hello. You are not audible. I'm not able to hear you. Is it my problem or everybody else cannot hear?
Not audible, actually not audible.
Not audible, right? So what we can do is you can write your doubt in the chat and we will take that up. Okay, so we have talked about neighborhoods. So before that, before everything, now you see what a neighbor is. What a neighbor is governs the objective function of that neighborhood, right? The way you define neighborhoods, you see the neighbors of 2-opt will be different from the neighbors of swap. If you are at this solution, the neighborhood of using swap will be different than the neighborhood using 2-opt. So you are in a way changing the landscape. In using a neighborhood may create multiple local optimas. Using another neighborhood may create a good big global optima, and all solutions will be in a plateau or something like that. So choosing which operator to use to create a neighborhood is very, very important decision to make. Okay, and that governs your landscape. That is why this visualizing the landscape is important. The operator you are using governs the neighborhood because the solutions in the neighborhood changes, and depending upon that solution the objective function will change. And if you select one kind of neighborhood, the landscape will be different. If you select different kinds of neighborhood, the landscape will change. So this decision is very important, and that is why I am telling you for traveling salesman problem to 2-opt, 3-opt, k-opt, these are better than swap or insertion or something like that. These are better neighbors for traveling salesman problem because that landscape has a good big global optima and very few, not very few, small local optima. Yes, Sharans.
Uh, Actually, the landscape would remain the same, I think so. Just that we would be translating to different points on that landscape.
Sorry.
Actually, the initial landscape would always remain the same.
No.
It's just that by using different methods, we would be translating to different points.
No. So there is one idea of distance. Where have I kept? I'll show you. So what is distance? Distance is the number of operators you are using. So you see, when you are saying neighborhood, those solutions are close to one another, right? So if you are at a solution S, if you are at a solution S and all the neighbors of that solution you can reach by one operator, one apply of that operator. So we will say that those solutions are close to this solution S. Those are in the neighborhood of that solution S. So suppose there is one more solution S1, which using swap is in the neighborhood of solution S. So from S, you can move to S1. So from S, you can move to S1 using one swap operator. Okay, one swap operator. But suppose if you are using 2-opt, so from S using 2-opt, S1 may move out of the neighborhood. So for example, so what will happen is your S is here. This is the neighborhood using 2-opt and S1 is here. You cannot reach S1 with one 2-opt operator. So earlier with one swap operator, you could move from S to S1. But using 2-opt operator, you are not able to move with one 2-opt from S to S1. So for example, my earlier solution was A, B, C, D, E, F, G, right? This is S. And this swap operator gives me a neighbor of A, F, C, D, E, B, G, right? Now you have to perform 2-opt to move to this solution. You see, you will not be able to use one 2-opt to move to this solution. You will not be able to do it, right? You will not be able to do it. You will
Sure,
need
sure.
two 2-opt. So the neighborhood is changing. S1 was a neighbor of S using swap, but using 2-opt, it is not a neighborhood. It is not in the neighborhood. So the distance is increasing. You may have to do 2-opt or 3-opt to reach to S1. So since the neighborhood is changing, the objective function values also change, right? So the objective function value for this was suppose this is objective function. So suppose S was here. This is objective function value, and S1 was this, and it was in the neighborhood. Now you see S is here and this is the neighborhood, but S1 comes here. So this has moved drastically, right? Objective function changes depending upon the solutions in the neighborhood. So you're changing the landscape. You see, this is not very important for this workshop. Okay, if you're not able to understand this, for
No,
everyone I'm saying.
understandable. It's just that by landscape, we mean the neighborhood influence.
So the landscape will change depending upon the neighborhood. That is the idea. By the way, for everyone else, I'm saying if you're not able to understand this, it is not very important to understand local search or simulated delineing. I am just covering this because this comes under the basics of metaheuristics. If you just want to apply local search into some problem of yours, you may not require to go into this much depth. So please stick with me. I will try to cover the other parts. But these are important concepts to understand meta-heuristics. Okay, so we have talked about neighborhoods of traveling salesman problem. How can you create a neighborhood of a knapsack problem? You can just flip a bit. So your representation is like this: 1 1 0 1 1 1, something like this. You flip one bit, so you say 0 will become 1. So this is one distance. This is known as Hamming distance technically. So this is one distance away. This neighbor is one distance away. Flipping one bit, you are creating a neighbor, right? For continuous variables, you can just take x minus delta and x plus delta. Okay, so choosing a neighbor, how to create a neighbor is important. A well-defined neighborhood is crucial for the success of the meta-heuristics. This is actually important. Huh? Okay, so examples of neighborhood: 2-opt, 3-opt, insertion, exchange, yeah, inversion. Exchange is actually swap, huh? Bit flip. Okay, so yeah, these are okay. Fitness landscape analysis, the things we were talking about is actually the fitness landscape analysis. Okay, there will be cliffs, values, plateaus, and so on and so forth. Distance, so defining the distance help you define the neighborhood. What is the size of your neighborhood? So you can take Hamming distance. It means 1 bit flip is 1 Hamming distance, 2 bit flip is 2 Hamming distance. Swap distance, 1 swap is 1 swap distance, 2 swap is 2 swap distance, and so on and so forth. You can understand this. Okay, you know, don't need to go into details, just get the idea. So over here we have finished all the basic concepts for single solution meta-heuristics. This is the last part, initial solution, then we'll move on to the single solution meta-heuristics. Okay, so what have we covered? We have covered how to represent a solution, what objective function should we use that guides the meta-heuristic. Then we covered how to handle constraints. Then we moved on to understand the fitness landscape, and then we understood neighborhoods. By the way, why are we talking about neighborhoods? That is because local search is actually performed in the neighborhood. That is why the name local search. It searches the local search. It searches locally. It searches only the neighborhood. It will not go to the whole search space and search for a better solution. It will start at a solution. It will search the neighborhood and then move to a better solution in that neighborhood. That is why the name local search. Okay. Initial solution. You see, every time I have mentioned about single solution meta-heuristics, we are saying we will start at an initial solution. So picking that initial solution is important. There are many approaches to do it. You can do it randomly. You can do it greedily like a knapsack problem. You can use a greedy heuristic to start with the solution and then move on to better solutions. Okay. Trade-off. If you go with a random solution, it is quick, but it may require more iterations to converge. Greedy solutions may take some time to obtain the solution, but convergence of the meta-heuristics will be faster. You can apply some hybrid approach that I will perform greedy search for some minute of time and then other things I will do it randomly, and so on and so forth. Okay, but this is important. Starting with an initial solution is important. Huh? Now we will start with single solution meta-heuristics. By the way, we have discussed local search a lot. So when we come to local search, it will not take you more time to understand. We have discussed this a lot, and it will become easy to understand if you are following. Okay, so what is single solution meta-heuristic? So this is a classification. Huh? Meta-heuristics can be, so this is one type of classification. You can have multiple different classification scheme as well. For this scheme of classification, it says we have two groups: single solution meta-heuristics and population based meta-heuristics. Single solution meta-heuristic means it's only sticks with one solution and moves to another solution which is better. So it only sticks with one solution at a time. Single solution meta-heuristics explores the search space by iteratively improving one candidate solution. It only sticks with one solution. Unlike population based meta-heuristics, they do not maintain a set of solutions. It always maintains one solution. Key characteristics: start with a single solution and modify it iteratively. Use local search techniques to explore the search solution space. We will talk about it. Typically faster and require less memory. So in population based meta-heuristic, you have to maintain data for all the solutions in the population. But in single solution meta-heuristics, you are only considering one solution, so it requires less memory. Often requires strategy to escape local optima. So we were talking about that there are local optimas and it can get stuck in local optima. So one strategy was to modify the landscape, but still after modifying the landscape, you may have multiple local optimas. So there are other meta heuristics which employs strategies to escape local optima. I will repeat again. We talked about that local search may get stuck in local optima. One strategy to escape local optima is to create a landscape that doesn't have many local optimas. Still, there may be multiple local optimas. So there are different meta heuristics, modifications of local search, which has the tendency to escape local optima. Okay, I hope that was clear. Key takeaway: single solution meta heuristics are simple, effective, and efficient and effective for many optimization problems, but require strategies to avoid getting stuck in local optima. Local search. We have talked about this a lot. You will be able to understand it. Maintain a single state and move to the neighboring state. Often provides good enough solution while conserving computation time. So we will take the example of traveling salesman problem. Okay. So this is the algorithm. So I have written the algorithm here. I have taken it exactly from this book. I'll try to make it understand and then we'll take one example as well. Okay. Before that, so suppose we are starting with a solution S naught. S represents the current solution. S is the current solution. What is current solution? So in single solution meta heuristic, we stick with a solution that is known as current solution. Okay. So initially, so this arrow implies that we are storing the value on the right hand side to left hand side. It is actually initialization or assignment, you can say. S naught is assigned to S. That is, current solution is actually the initial solution. So we are starting with S naught and current solution takes S naught. Okay. So we are starting with the initial solution while the termination criteria is not met. By the way, I have not talked about this, but this is also important. When to terminate? I have not mentioned it over here. I will make one slide tomorrow because you should know when to terminate. Okay. Until the termination criteria is met, do the following. Until the termination criteria is met, do the following. What we have to do? We have to generate the neighborhood. So n of S is the neighborhood. This is the neighborhood. NS means neighborhood. Generate the neighborhood. If there is no better neighbor exist in this neighborhood, if there is no better neighbor that exists in this neighborhood, stop the search. So this is also a termination criteria. No better solution exists in the neighborhood, stop the search. Output this solution and it is a local optima. If there is a solution which is better than S in the neighborhood n of S, if there is a solution S dashed in the neighborhood NS which is better than S, then move to that neighbor. That is, S will be replaced from whatever it was to S dashed. We replace whatever was in S with this new solution S dashed. Okay, and then repeat. Generate the neighbor of this new current solution. Check if there is a better solution. If not, stop. If yes, move to that solution. Okay, so this is how the algorithm has been written. Any doubt? Okay. So I have taken a traveling salesman problem example. Yes, it's very simple. You can just see this is the starting solution, initial solution. These are the distance I have mentioned. This is the total objective function value of this solution. And this is known as the current state or current solution, whatever you name it. Create the neighbor. So we are using what neighborhood I am using? Swap neighborhood I am using. So I'm creating swaps. So I have only given 3. You should exhaust it. This example is not actually accurate. You should create all possible neighbor of the current solution. I have only written 3. So this is actually not appropriate, not accurate. So create all the neighbors of this solution, search the neighborhood, move to that solution. Okay. So I have only depicted 3, but this is not correct. none of the neighbors improve. This is the current state remains. Okay, I'll just remove this. I think it is not appropriate, but you get the idea. Okay. Right. So we have completed local search. Any questions? Yes, Sharans.
So in the local search algorithm that you mentioned, so when we will be checking for another neighborhood, we need to find all possible neighborhoods, or even if we get one better neighborhood, we will switch to that.
Okay, so good question. So I have mentioned that in this slide, strategies for selecting a neighbor. So there are many different strategies. First is best improvement, that is exhaust all search in the neighborhood. Select the best neighbor in the neighborhood and then move to the neighbor. Another strategy is to select the first better neighbor. So if you are searching the neighbor, select the first solution which you encounter has a better solution, move to that neighbor. So this has trade-offs. In the initial strategy, when you are moving to the best neighborhood, you are spending time exploring the neighborhood and then moving to the best. In the other strategy, first improvement, you are not spending time. You're saying that I will explore the neighbor one at a time, explore the neighborhood one at a time, one solution at a time. Whenever I encounter one neighbor which is better than my current neighbor, current solution, I will move to that solution. I will not exhaust the neighborhood. This saves time. But I'll not say it is one is better than the other. You can choose whatever you want, or you can have random selection. So what you can do is you can instead of systematically generating neighbor, you can randomly generate neighbors and then move to a solution. So there are other strategies as well. I have listed down 3. Is that this answers your question?
Sure. Thank you.
Okay, so why is this slide after this slide? This is because there is something called intensification and diversification. Intensification means focusing on that solution and exploring only that region. Diversification means focusing on the larger spaces. You move to some other space and so on and so forth. So local search, best improvement, when you are searching for best improvement, you are trying to intensify. You are trying to say, I think this is where my global optima is. I will perform best search over here and I will only search that space. Diversification means you're trying to avoid local optima. You think that, okay, maybe I'm stuck in local optima. I have to move to another solution, which may lead to global optima. This might not make sense right now, but this is an important concept to understand. When we discuss simulated annealing or maybe population-based meta-heuristics, this will become more prominent, more important. Okay, so we will come back to this intensification and diversification. The idea is intensification is you are thinking that, okay, this neighborhood looks interesting to me, it looks promising. I will only stick to this neighborhood, I will not move out. Diversification means you are trying to explore the search space a lot. So for example, what you can do is at the start of your search, you can diversify. You can search many areas, but when you come up to one area, you will say, okay, I will stick to this place and I will try to find more intricate neighbors. That is the idea. It will make more sense if we talk about simulated annealing. So before going that, strategies of improving local search. So you see, local search has a tendency of getting stuck in local optima. It is highly dependent upon the initial solution. The initial solution governs where the local search will converge, right? So there are many strategies of improving local search. One way is to iteratively perform the search. You start with one solution and so the local search terminates. Again, you randomly start with another solution. Your local search will terminate. So you are diversifying. You see, you are starting with one solution, doing the local search. When it terminates, again, you randomly generating some other solution at some other place in the landscape. Then you are performing local search. Then you are terminating the local search. So you're in a way diversifying. You're trying to escape local optima. So that is known as multi-start local search. You are randomly starting at different initial solution. You are randomly starting at different initial solution. You're changing the initial solutions. Iterative local search is a little bit different. What you do is you start with a solution, you come to the local optima. When the local search terminates, you modify this local search solution little bit. You change the solution little bit, move to another point, and then again you do local search. When you come to that point, you modify the existing solution, that local search solution, a little bit, and then you again perform local search. So it is not randomly starting at any point like multi-start local search. This is actually modifying the local search solution. So it is iteratively searching the search space. Okay, so this is one strategy of escaping local optima. Another strategy is to change the landscape of the problem. So we discussed one part of this. Change the neighborhoods. Different neighborhoods. If you use different neighborhoods, the landscape will change and local search will get to different local optimas. Another strategy is to modify the objective function. You see, I told you that objective function is what governs the landscape. So you can add a penalty to the objective function with constraint or something like that. There are other methods as well. We will not go into deep. So there are two ways to modify the landscape. Either change the neighborhood or modify the objective function. Do something, add some term to the objective function, which is governed by the solutions, and in a way you are changing the landscape. We don't need to go into that. These algorithms are known as guided local search, noisy method, or smoothing method. Different neighborhoods, which I was telling you, variable neighborhood search. There is another algorithm known as variable neighborhood descent. There are two algorithms over here. So this is one more method. So what are the two methods we discussed? Start at different solutions at a time. This is one method to improve local search. Another method is change the landscape altogether, right? One more strategy is to select non-improving solutions. In local search, we are always selecting a better solution. What if we select a non-improving solution, move to that, and maybe we will move to a better local optima? The two algorithms that comes under it are simulated annealing and taboo search. These are all modifications of local search. Simulated annealing is a modified version of local search. Taboo search is a modified version of local search, and all these algorithms which are mentioned over here are some way or the other modifications of local search. So simulated annealing as well as taboo search accepts non-promising solution, accepts non-improving solution, and then tries to move to a different local optima. Any questions? Any questions? Any questions? Okay, thank you. So I'll come back over here now. Representation, we have understood. Yeah, just give me a 1 minute. Objective function, constraint handling, state space search and neighborhood, initial solution, single solution based meta heuristic, local search. If we come over here, the plan of the workshop. So this was the plan of our workshop. Simulated annealing and taboo search we will discuss tomorrow, and then we will perform hands-on using Python programming. You don't need to install anything in your computer. We will use Google Colab. It is a web platform where you can do Python programming directly over there. Okay, and if you have some IDE of Python, you can use that, or if you don't have, doesn't matter. Okay, so simulated annealing and taboo search we will discuss tomorrow, and we will do hands-on practice on these algorithms. Maybe I'll do one or two. We will see depending upon time. And then on Sunday we will move on to population-based meta heuristics. I don't know if I'll be able to cover ant colony optimization. We will see, but I'll give you idea. So this is the end of today's content which I had planned. Yeah, Souvik.
Nice presentation. My question is, can you just tell me of the smoothing method just you told? What is that thing?
These things, these are actually modifying the objective function. The book which I have given, it has detail of all these algorithms. So if you want to read more, download that book, you read it and we can discuss it later maybe.
Okay, okay, sure. Thank you, thank you, thank you.
Mm.
Yeah. Hi, Shubham.
Yes.
Yeah, my name is Aradhana.
Yes.
Actually, I'm pursuing my research in the area of behavioral finance.
Okay.
So, one thing I want to ask that how can I implement this or in some or the other way in my area?
So that is a difficult question to answer. I have limited research experience. So if you are in some kind of search algorithms where you are trying to find, so for example, in finance, you are working with some decisions to make such that the cost is minimized or something like that. I'm giving an example of finance. I know it's not your area still. So in those areas, if you are working with such kind of problems where you are searching a solution, those areas you can use. I have very little idea of this, so I'll not be able to help you now.
No issues. Well, thank you so much. Very nice presentation. Although this is not my area, but still I'm getting interested to that.
Thank you. That's a pleasure. So I wanted to, actually, I have tried to make it as basic as I can. So it is just covering the basics. If you want to read more about this area, you can read it in the book.
That
So I
is what
hope.
simplicity is what attracts me because since this was not my area, I'm not from the mathematics, but you are explaining in such a good way that I thought of, attending this workshop so as to add to my knowledge.
Thank you. Thank you so much. It means a lot. Yeah.
Actually, what it was the question was asked. Actually, the problem we are facing in every one of our domain, making the mathematical model of our problem. If we can make the mathematical model, then we can think of next how to uh, optimize and which tool we should use. So
Okay, so basically, sir, you're saying that if I can, make the conceptual model of my research into the mathematical modeling, so I can apply these, right?
yes, something like this, like
Sir,
what the variables we should consider, what should be the span of the variable or feasible domain of that those variables, and then how to make it mathematical model. That is very important, I think. What Swam can
So
say in
one
details.
correction, one correction. So for applying meta heuristics, you don't need a model. So there are
No, but
problems.
which variable we should consider, like
So
when you are
for example,
considering node as some point,
right.
branch as something. That is the mathematical model we have to frame for our
Right.
problem.
So
I
one
am not
example.
telling I am not telling exactly the analytic means equation we have to form.
Yes, sir. Yes, sir.
I am
Yes,
not
sir.
telling we have to make a complete numerical model, not numerical model, but what are the variables, how they are connected, giving weightage. That part I am telling as the mathematical formulation.
Yes, yes, sir. Correct, correct. So we have ended
Hello,
at
sir.
correct time. Yes, yes. Sorry. Continue.
Sir, can we get this PPT slide there?
Everything is
Actually,
uploaded in
today
a.
only I joined the WhatsApp group, so I don't have any material. Can you post it again, sir, please?
So you can go to the group description. There is a link. I have a small website where I post everything. So you can go there and see yesterday's lecture as well. That has also been uploaded there.
Can you come again, sir? Sorry.
So in the WhatsApp group, there is a description where I have mentioned a link. So that link is to my website and I upload all materials, including the recordings in that website. You can go and visit that website, get the PPTs as well as recordings in there. You can watch yesterday's lecture as well. It has been uploaded.
Oh, thank you so much, sir. Thank you so much. Yeah, yeah, this
Please,
is I
please
have
call
used
me
polar bear
Shubham.
optimization in my research, sir. I'm understanding everything. It's very nicely you are explaining the things. Thank you.
Thank you. Thank you so much.
Uh, so one thing you can do, I found that 3 participants have joined after we have, uh, I have turned off the attendance. Okay. So if you can share that code, and
Yes,
whoever
sir.
has joined, if they can give the attendance once more.
Yes, sir. Yes, sir.
Yeah, thank you. So let me, I am trying to open the Google form. Now it will not accept the response. Just wait, I am opening. After that, you please give your attendance.
Okay,
Or
okay, sir.
so I'm at your end also, if you can open the acceptance link,
Okay, I'll do that, sir. I'll do that.
if possible, please. Okay, it is open. Yeah, now it is open. You can, whoever has joined late, you please give the attendance. You have to enter this code MTH2275.
So your feedbacks are most welcome. It will help me. Actually, yesterday I read few of the feedbacks, and I what I understood is I was able to convey most of the parts, but there are few participants who are not coming from this operations background or optimization related background, so they are facing trouble to understand the concepts. Um, if you could unmute or speak whether today's lecture was okay or not, so it would be good. Yeah. Or maybe if you don't want to speak here, you can write it in the feedback form which is there in attendance sheet.
So
I shared
if
my feedback with you, Shubham.
Thank
Since
you.
I'm not
thank you.
from this background, but I like this workshop, very interesting, and the way you explain the things is
Thank you.
very nicely explained. And you uploaded all the videos as well as the PPTs on your website. I have gone through your website. That's very kind of you,
No,
and
no
that too
problem.
very promptly because I've rarely seen a person who uploaded those on the same day. So that
No,
is very kind of you.
thank you. Thank you so much.
Yeah.
Okay, so if any more question you is there, please ask, or else we shall end the session here.
Okay, so I'll end the session now. Thank you for joining. See you tomorrow. Huh?
Thank you, Sumant.